Hey everyone, welcome back. In this video, we're going to do an example of a related rates problem. In this problem, we are told a water tank has the shape of an inverted circular cone. It has a base radius of 2 meters and a height of 6 meters. The tank is being filled at a rate of 3 cubic meters per minute, and we want to figure out how fast is the water level rising when the water is at a height of 3 meters inside of our tank. So like with all these related rates problems, the first thing I like to do is identify what we don't know and what we're trying to figure out, as well as what information do we know that will help us find that quantity we are looking for. In these related rate problems, we're always trying to find out some rate. So what we want to know is going to be some rate. What rate are we looking for? And we can always kind of shortcut to the end most of the time to figure out what it is. That last sentence is telling us what we're looking for. It says, how fast is the water level rising? So we're trying to find the rate of change of the water level. If we call the water's level H, or like let H describe the height of the water inside the tank, then what we want to know is dH dt. The derivative of the height of the water in the tank with respect to time is going to tell us how fast the water level is rising. So let's see. What we do know is that our water tank has the shape of an inverted circular cone. In some examples, a picture isn't necessary. This is going to be one of those examples where I think the picture is going to help us out a lot, not just for organizing our information, but for actually making progress within the problem. What else do we know about this cone besides its shape? We're told it has a base radius of 2 meters. So that circle up at the top has a base radius of 2 meters. And as we kind of go down the cone, or as the water level changes, we can see that that radius is going to shrink as you move down the cone. So let's see, the cone also has a total height of 6 meters. We're told the tank is being filled at a rate of 3 cubic meters per minute. So what kind of quantity is that describing? The units can usually give it away if the rest of it does not. So if we look at those units for this rate, we have cubic meters in the numerator, that's volume, and then we have minutes in the denominator, that is time. So that rate must be describing dV dt, the rate of change of volume with respect to time. We know that that is 3 cubic meters per minute. Let's see, we're also told that at our moment of interest, the water level is at a height of 3 meters. So we also know H will be equal to 3. This is all we are given in the problem statement, but there's a few other pieces of information we're going to need, right? So we have the dV dt quantity, or the volume quantity is going to be involved at some point. We also have the H quantity. And so now we need to kind of relate the volume and the height of our cone together. And the way we can do that is using the general volume equation for a cone. We might have to look this one up, but the volume for a circular cone is given by 1/3 pi r squared, or 1/3 times the area of the base times the height of our cone. So if we look at the information that we have gathered so far, we can see that we have our equation that relates the volume and the height together, but it also involves the radius, and we weren't really given much or really any information about the radius or how it changes in this situation. So we're going to have to work around that. What we're going to have to do in this problem is figure out basically how to get rid of the radius, or how to express it in terms of one of these other quantities, in particular, the height. We could wait till later to do that, but then we'd have to differentiate this, and we get derivatives involving v, r, and h together. It's actually going to be much simpler if we try to get rid of that r earlier. So how do we get rid of that r? How do we express r in terms of h? That's where our picture is going to help us. We know at our moment of interest, the height of the water level will be 3 meters, but to help us find the relationship between r and h in general, let's just go ahead and think of the height of the water level as a varying quantity. Well, then that can give us this kind of smaller cone inside of our larger cone, or this smaller triangle inside of our larger triangle if we're just looking at the side profile of our picture here. And we know for a given h, as the water level varies, there will be some r value that corresponds to that given h. That'll be like the radius of that cone of water inside of our overall tank. And here we can use the idea of proportions and similar triangles to help us figure out the relationship between the height and the radius, right? We can see this little yellow triangle is the same shape, just a different size or scale of our larger blue triangle when we look at our side profile here. And so that means these triangles are going to be similar, and similar triangles have that relationship that their side lengths are proportional. Or another way to say that is if we take any ratio of the side lengths between these two triangles, it'll be constant. So that means if we take the ratio of the height to the radius in our little yellow triangle, that ratio will be the same whenever we look at any other similar triangle to our yellow one, including our large blue one. If we take that same ratio of the height to the radius, we get 6/2. The ratio between the height and the radius is 6:2 or 3:1. So h/r is equal to 3. That's just simplifying 6/2. And now we can solve for r and write it in terms of h if we just move things around a little bit. Multiply both sides by r and then divide both sides by 3. And we find that the radius is always going to be 1/3 of the height. We can see that very clearly in our large blue triangle. But because all the other little triangles are going to be similar to that large blue one, that's going to be the relationship for any radius and height as we fill this tank up with water. So what that allows us to do now is go back to our volume equation here and express it in terms of just the quantities we have this information about, the height and the volume. So we have 1/3 pi times the radius squared. We're going to replace that or substitute it with h/3 squared. So we'll have to square the numerator and the denominator. That'll simplify to h²/9. And so now our volume equation is 1/3 pi times h²/9 times h, or we can rewrite that as pi times h³/27. All right, so now we have the volume written in terms of just the height. Those are the two quantities we either want to know about or already do know about. So now we're ready to take this relationship between the volume and the height, differentiate it implicitly with respect to time, and use that relationship between the rates to find dH dt. So let's make some space and get that done. All right, so now we're ready to differentiate our equation. We're going to differentiate implicitly with respect to time on both sides of our equation. And so if we differentiate the left-hand side, that's the easy side, that'll just give us dV dt, or the rate of change of the volume with respect to time. And if we differentiate the right-hand side of our equation, we're going to be a little bit careful in how we do that. We think of h as a function of time, so we're not going to use just the power rule to find the derivative of the right-hand side. We're going to use the power rule in combination with the chain rule, or you can think about using that generalized power rule. So the generalized power rule says, take the derivative, bring it out front. That'll give us 3 pi h/27. We decrease the exponent by 1, so that turns into an h². That's where the normal power rule would stop, but we're using that generalized power rule, or the power rule in combination with the chain rule. And so now we have to multiply by the derivative of our base, or the derivative of that inner function. And that's going to give us the derivative of h with respect to time. Okay, so at this point we could simplify our equation, or maybe solve for dH dt symbolically, but sometimes, and in this case, it's going to be a little bit quicker and easier if we now just plug in the information we know and then solve for the quantity we are looking for. So let's see, we should know all this information except dH dt, and sometimes when you do these problems, you'll get to a point like this and realize, oh, you're missing a piece of information and you have to go back and find it, right? If we had not taken the time to rewrite our volume equation in terms of just h, but involved both r and h, that's where we'd be at one of those points where we'd see we don't have enough information to progress any further. So we have to go back and figure out what to do. But we know what to do here. We just got to plug in our values. So let's see. dV dt was equal to 3. Then we have that equal to 3 pi times the height of the water level at our moment of time. But that was also 3. And then the only thing left is that unknown quantity, dH dt. So let's see, let's go ahead and simplify this as much as we can. And actually the right-hand side simplifies very nicely because we have 3 factors of 3 in the numerator. Those multiply together to give you 27, but that just cancels out that factor of 27 in our denominator. So now our equation is looking like 3 is equal to pi times dh dt. So we can isolate and solve for dh dt just by dividing both sides by pi. So dh dt is equal to exactly 3 over pi. That is how fast the water level is rising. That's going to be 3 over pi. Let's see, our units should be meters per minute, but no one describes heights using pi's or factors of pi. So let's approximate that. 3 over pi is approximately 0.955. And again, our units for this rate are the units for the height, which were meters, over the units for time, which was minutes. So now we know exactly how fast the water level is rising at this moment of time. It is rising at a rate of about 0.955 meters per minute.